Hi, everyone, and thanks for joining us. The topic we're going to talk about today, it sounds a bit esoteric, but it really isn't. It's accuracy in measurements, specifically in laser measurements, when, why, how, and you'll be surprised to hear there'll even be a little bit of a when, maybe not. We all are, technology professionals, so we can all appreciate that quantifying things is the only way to give them any meaning, at least in when it comes to science and technology. And when it comes to photonic measurements of lasers, there are a lot of critical processes that depend on a whole bunch of numbers being very specifically what they were meant to be. So we're going to be talking about that. I'm assuming you're at least a little bit familiar with Ophir. Our goal here, by the way, is not to push, an Ophir product of this type or another type. I did put a lot of effort into keeping the information as generic as possible. But just in case you don't know who we are, we've been doing this for like many tens of years. Some years back, we were acquired by Newport, and some years after that, Newport and us together, we became part of MKS. Basically, what it said in that slide, if I can summarize it, is that we like to do the hard stuff that you would appreciate getting off your head so you can focus on your work and not have to lose sleep over the tools you're going to need to get your work done. I think that's a pretty fair summary. Okay, our goal here is not to turn anyone into a measurement instrument design engineer. As much as I love talking about the engineering aspect of things, we're not going to go into any great engineering depth. And I don't want the topic to be anywhere near as esoteric as maybe it sounds. So I hope that I've found the optimal balance between breadth and depth. So here's what we're going to be talking about. We're going to, first of all, so that we're all speaking the same language and all on the same page, we're going to just talk about the meaning and the importance of accurate measurement and calibration of measurement, and when and how that could make a difference. And as I hinted earlier, we'll even allow ourselves to admit that sometimes maybe it doesn't make such a difference, but it's important to know when yes and when no. In most data sheets of measurement instruments, you'll find a specification of the accuracy, and we're going to look at where those numbers come from. Now, don't panic. We're not going to go into any, again, great deep analysis of exactly where each one of those numbers come from, but I do want to look at it conceptually so that you'll have some appreciation of what goes into it, and I will point you in the direction of more detailed information in case it's of specific interest to any one of you. And then we'll get into some best practices of how to maximize the accuracy that you can get from your measurement instrumentation. We'll say a few things about what a manufacturer of the instrumentation like Ophir does before it reaches your hands to try to make it as accurate as possible, and then some best practices that you can perhaps adopt where practical so that you can get the most trying to find a suitable version of bang for your buck, most accuracy for your buck. I don't know, it doesn't sound good, but whatever, you get the idea. So as I said, I'm keeping this information as generic as possible so that it'll be as helpful as possible to as many of you as possible. You can appreciate that where I bring real life examples of actual instruments, then obviously I'm going to be looking at Ophir instruments because obviously those are the ones that I'm able to speak about. So let's begin with the beginning, and a good place to begin is defining our terms, and you'd be surprised, or maybe you wouldn't, at how often just this step can preempt a lot of potential issues. So accuracy, that's kind of a relevant word for our discussion, or sometimes it shows up as measurement accuracy or power accuracy if it's a data sheet of a power sensor. These definitions aren't rigorous, but they're somewhat rigorous. How close the measurement result I'm getting from this particular, let's say, laser power meter is to the absolute truth. Now, those quotation marks around absolute truth, you need to imagine here some kind of a musical note like da-da-dum or something. Now, what is the absolute truth? I, for one, don't really have access to too much absolute truth. So we all understand that when we talk about how close something is to the absolute truth, what we mean is to a suitable reference that we all agree that we're referring to. So when it comes to laser measurements, in most of the world, we all understand that we're talking about the American NIST, National Institute of Standards and Technologies, if I remember right. And we all agree that when we say how close the measurement is to what it really should be, what we mean is how close is it to what NIST would say it should be, plus no measurement can ever be perfect. And in NIST's measurements themselves, there's also a certain degree of uncertainty. Horrifying thought, but that's the universe we live in. So when I'm talking about how close my measurement is to the absolute truth, let's say if I measure the power of a laser beam as 1 watt, how close is it to the real power of the beam? Well, I don't know the real power of the beam, but our measurements are traceable to NIST, and NIST themselves also have a certain degree of uncertainty. Okay, I like the sound of that. So that's just something to keep in mind. Some of these things, at least on this part of our conversation, again, might sound a little esoteric, but they're kind of basic. Calibration uncertainty. Okay, calibration uncertainty is, well, you can read it, what it says here, but let me just maybe explain it verbally a little bit better. As it appears on our documents and our data sheets, our COT certificates, it specifically refers under the ISO 17025 standards to which we're certified. Okay, I'm going to say a little bit about that soon. It's a certification for a calibration laboratory. That refers to our calibration process itself. The specified, let's say, power accuracy or measurement accuracy, as the case may be, in the sensor's data sheet includes additional stuff besides just the uncertainty in the calibration of that sensor. There's other stuff. There's a contribution to the final uncertainty that comes from the meter, the display. There's all sorts of factors that contribute some uncertainty to the final number that I'm getting out of my measurement device. These are all nuances. I'm just mentioning it. That's not going to really be the focus. I will mention that I bounced all of this material off our R&D physics team leader, who was the guy who led the process of us getting certified to ISO 17025. So he helped me find the right balance between being overly pedantic to the point of being geeky and being at least accurate enough, pardon the word, so that we're speaking truth. So for example, your instrument tells you that the power in this beam is 1.0 watts. If the data sheet says that that instrument is accurate, has a measurement accuracy of plus minus 3%, it means that the true value, okay, you remember that musical note there, is expected to be somewhere between 3% above and 3% below that 1 watt. So it might be anywhere as low as 0.97 watts. It might be anywhere as high as 1.3 watts. And even that, we're not saying it absolutely. There's a 95% confidence level. Everything here is statistical, again, because none of us, most of us, don't have access to that absolute truth. So everything here is always going to have these riders, approximately 2 sigma standard deviation. It's just, again, something to keep in mind. Sounds a bit like hair splitting, but it's just something that is important to keep in our vision. It's important to differentiate between accuracy and precision. This is actually not at all theoretical. This could be, in some applications, make a huge difference. I'm going to explain what I just said momentarily. So accuracy is what we just said. It's how far our measurement is from the that true value that the measurement should have had. And obviously, we'd like that to be as small a number as possible. So for typical Ophir laser power sensors, typical measurement accuracy in the data sheet might say something like plus minus 3%. For the very high power sensors, for the multi tens of kilowatts, it might be plus minus 5% and something. And then there's going to be a few additional errors in the data sheet. This might say additional uncertainty due to frequency effect might be another plus minus 1%. Your tolerance on uniformity across the sensor surface, another plus minus 1%, whatever. All these additional sources of potential error sometimes combine linearly, like 3 plus 1 plus 1 plus 1.5, and sometimes they get combined statistically, root sum square. It depends. Let's not get bogged down, but it depends. Basically, it depends on how random each of these sources of error is. So that's accuracy. Precision, on the other hand, sometimes referred to as repeatability, is a measure of, given a whole bunch of repeated measurements of a perfectly stable and unchanging laser, how repeatable are my results going to be? And in the universe that we live in, never 100% repeatable. So the precision or the repeatability is how wide this curve is, the spread of my measurements, assuming that the thing that I'm measuring actually stayed perfectly stable. Accuracy is how far that is from the true value. So I might have very high repeatability, even though it might be way off of the absolute truth. In some applications, that might be okay. We'll say a few words about that a little bit later on. Calibration. Oh, and yeah, this is also important. The precision is in the best case going to be limited by the inherent noise in my measuring device, because that's going to impose a certain randomness that I can't control. There are obviously going to be other factors as well, environmental factors. So for a typical laser power sensor, the repeatability is up to plus minus 1%, usually closer to plus minus 0.5%, assuming my environment is stable. If I'm using a thermal type sensor, which is typically used for measuring laser powers of like maybe, let's say, milliwatts and up. So the thermal stability of the environment might make a difference. But if the environment is stable thermally, there's no air conditioner blowing directly on, onto the sensor and so on, then I can probably expect repeatability to be maybe plus minus 0.5%. Again, these are statistical numbers. So let's talk about calibration. Calibration is the process of comparing a measurement of a device under test to some kind of a known reference, traceable to NIST typically, to determine if it's performing within spec. So I might have my NIST calibrated reference sensor. At Ophir, we call it a master sensor. And then I take my production sensor that I just finished manufacturing, and before shipping it out, it goes through calibration and then quality control and that sort of thing. So in my calibration, I take a measurement of a laser with my master sensor, and then I move the master sensor out of the way. I put the sensor under test in its place, and I take another measurement, assuming that the laser itself has not changed. We have, we use stable lasers for this, and I see, oh, my unit under test is reading only 30% of what the master said. All right, I've just calibrated that sensor. Calibration can include adjustments. It theoretically doesn't strictly have to, because as long as I know the correction factor, then I can use the sensor now. Obviously, standard catalog sensors that get shipped out the door of any manufacturer like us of measurement instruments will be adjusted so that it actually reads the same as that master sensor, as close to as possible. Again, nothing's perfect. And as is clear from what we've just been saying, it inherently assumes and is based on there being some kind of traceability to an accepted standard. Because if I say that this is accurate to within plus or minus 3%, well, 3% of what? So on our data sheets, on our certification and all that sort of stuff, we'll say, traceable to NIST, it might be PTB, it might be, whatever it is, as long as we all agree about what the reference is when I say that I'm within plus or minus 3% of it, then we're good. And valid for a limited time. Again, the universe that we live in is made of matter. We're going to see momentarily why I'm emphasizing this. Momentarily is actually now. So now with what we've just said, we can go ahead and answer the question that heads up this section. Why maybe is accuracy important? So all lasers and delivery systems degrade with time and use, at least the ones that are made of matter. Okay, I'm not too aware of other ones. And as we all painfully know, everything and everyone made of matter degrades with time and use, but we're not going to go there. So let's see what that means. There's a schematic drawing, pardon my artistic skills or lack thereof, of a typical materials processing application. So in order to melt, vaporize, otherwise zap, whatever the given material, we have a laser beam, and we have a beam with a given power and given wavelength and okay, obviously. And we want that beam to be focused down to a given diameter so that the power density is high enough to melt, weld, cut, zap, vaporize, whatever the workpiece, to do the work. And here, I hope you can see my cursor moving. Here is the space within which the power density is within the right range to get the work done. And our target surface, our workpiece, we're going to place it somewhere right over here. I'm dreadfully oversimplifying this, obviously. Now, we design and program our systems so that a user is going to punch in some given application, drill a hole of type so and so and so in such and such material. And the system is going to set up the exact electrical parameters such that a beam with the exact optical parameters will be generated and it'll do the work. But what happens if the power drifts due perhaps to aging of components, or let's say heating effects change the optical characteristics of the focusing lens and the focus shifts? We could suddenly find ourselves with the target surface no longer inside the space within which the work can get done. Parameters that are not controlled can change what the process is doing and where it's doing it. That can make your process unpredictable, and that's a word we don't like. If we're talking about a medical process, a surgical system, or manufacturing some medical device, well, there's obviously a potential safety risk to a human being. In the case of an industrial commercial process, it can eat into the profits that it's supposed to be generating. Now, if what we're doing, for example, is producing small handheld laser pointers for use in an office presentation, then maybe just a one-time measurement for design validation might be enough, and we might not really need to worry a whole lot more about the accuracy. If it's a 0.5 milliwatt that comes out of the laser or 0.45 milliwatts, it might not really make such a difference. Don't tell anyone you heard me say that. But that's how it is. So obviously one needs to apply some common sense and understand one's application. So in some applications, repeatability might be more important than actual accuracy. It depends. When we have a process, cutting, drilling, a medical process, dental laser in this particular image, when the process depends on the absolute power or energy or power density per unit, per square centimeter, whatever, reaching a target surface, then obviously we need to know pretty accurately what the absolute number really is. And then we're going to need to have some way of monitoring the actual power or energy. And where we want to do that monitoring is also going to be a question that's going to depend on the nature of the application. So sometimes it'll be power, sometimes power density. We need to understand, and as owners of a given process, a process might not be an industrial, it might be a research thing that we're doing, whatever the case may be. We each know what the critical parameters are that make our particular process happen. So in the so-called drawing that we just looked at, it was power density, power per unit area, but it might be something else. So we have some customers, for example, that manufacture medical laser systems, and they have many tens of parallel production lines and quality control test stations at the end of each. For them, it's actually more important to keep track of the repeatability, the consistency of their measurements, more so than knowing the actual number. They're making medical laser systems, and these medical laser systems are, approved by the FDA, and they have a CE marking and that sort of thing. And if a particular system has been on the market for 5 years and it's doing great, and the measurement of the laser at the end of the production line says that this laser produces 10 watts, and the truth is it's really producing 12 watts. But if that, whatever it is that it's been producing for the last 5 years is exactly right, then, I mean, obviously they're going to want to know the real number, but much more important is that they're going to want to make sure that all of their measurement devices are agreeing with each other, so that they know that nothing has changed from what it's been doing so successfully for the last 5 years. See, these are all little nuances, and a manufacturer like us of the measurement instrument, obviously we can't know that. It's the nature of the application. Now, let's say you're being good and you actually build in a small sensor that samples a part of the laser beam, inline, let's say a small internal sensor mounted behind the rear mirror of your gas laser, or a small beam splitter that sends off 1% of the beam coming out of the laser into a sensor. So you're actually, you're doing well. But even that in many cases might not really give you what you need. Why not? Well, first of all, it will pick up changes, unwanted changes in what's coming out of the laser, but it won't pick up changes that happen farther downstream, misalignment of some of components in the delivery optics, or process debris that got deposited on the focusing lens and stuff like that. So you may need to have a constant monitoring at the target plane, or you may be okay using an internal monitor, and once every X time, measuring at the work surface. Again, every application has its own particular needs. Here you see a serial number that was, it's actually a mirror image, that was laser marked into a jet engine blade. It's a customer I visited some years back. In that industry, there's an industry requirement for every blade in a jet engine to be marked with a serial number in case, God forbid, there's an accident that turns out to be a result of a faulty blade. They want to be able to trace it back to the shift, the machine, the operator that produced that blade, so that they can run anywhere in the world they need to and do preventive maintenance. So one of their customers required of them to have some kind of a procedure in place of monitoring the health of their laser marking system, which was one of the last steps in the whole production line of these blades, so that they could catch any beginning of a problem early enough to do preventive maintenance and not cause an expensive delay of an expensive shipment because of a little thing like that. So they approached us, and we worked together to put together a suitable program. So sometimes it's easy. It's a regulatory requirement, medical, FDAC. In most cases, or many cases, it's not necessarily a regulatory thing. There are no calibration police out there. But let's say if it's an aesthetic, non-medical application like IPM, like IPL, intense pulse light, if you're not familiar with that, don't worry. So if you're dealing with humans, obviously you don't want to endanger your clients, even if there's no law about it. In many cases, it might just be a practical, commercial industrial consideration. What you see here is the right word, photomicrographs, whatever. A photograph through an electron microscope of via holes in a silicon wafer. Very, very small mistakes in that industry cost somebody very, very much money. So they've got a tremendous interest in catching everything and catching it as early as possible. All sorts of different processes like that. So it might be a practical requirement. It might be a self-imposed industry requirement. It might just be good sense to keep your yield as high as you can, so that you don't eat into those profits. Might be a requirement of your ISO 9000 certification, depending on what you're doing. If anywhere in your supply chain or your customer chain there is some sort of a government thing, a military thing, you might need to meet certain requirements imposed by that laboratory calibration standard, ISO 17025, and so on. Okay, I want to say just a few words, as we mentioned, where these specified accuracy values come from. We're not going to go through the math of every single one of these parameters. I just want to show you how the concept works. And as I said, I'm going to point you in the direction of more detailed information if that's of interest. So here we've got a generic calibration procedure. I'm, again, dreadfully oversimplifying this. We start off with a very stable laser. I'm going to explain momentarily why I just emphasized that. And here's that master that we sent to NIST for them to calibrate. We paid a bomb. It took a long time. We got it back. That's our first generation reference. We call at Ophir, we call that our gold master. We take that gold master and we calibrate some other new sensors against the gold master. Those are now the second generation. We call those silver masters. The gold master we then lock away in a cabinet. I mean, that thing's worth much more than its weight in gold to us. And in the day-to-day workings of our calibration laboratories, it's the silver masters that we use to calibrate the, our sensors that come out of production or that get sent in for their annual recalibration or anything like that. Periodically, we'll take out the gold master and compare and just do a check on the silver master to make sure nothing's gone wrong. Okay, not going to bore you with all the gory details of how we work, but you get the general idea. And the production sensors, as I said, are calibrated against these silver masters. So we put the master in the beam, we get a reading, then we quickly move it out of the way and replace it with the sensor under the unit under test, the sensor that we're calibrating. And we're gonna, in our case, we do adjust it. We don't merely compare it. Although in some OEM sensors, for example, that have an analog output, then we just do the comparing and we provide documentation, whatever the application needs. But in this case, we put the unit under test into the beam in place of the master. And now we get a reading and we adjust it so that it reads the same as the master. Now, you know what's coming next, right? As close as possible, because it can never be 100% exactly the same as the master. Now, if we're talking about thermal type sensors that we use for measuring power, we also use those for measuring single shot energy. We then need to add another step, and that's the energy calibration. So to create that pulse whose energy we're going to measure, we actually use a CW laser and we use an electronically controlled timed shutter to create the pulse. It's just that, such pulses are much more stable than they would be coming out of a pulse laser. Again, I don't want to bore you with the gory details. The overall uncertainty at the end of the day is going to depend on a number of different factors. Some of them are, first of all, the stability of the laser, because if the laser changes during that half a second, I guess, that it takes to do that switch, then I'm measuring a different power than the master measured, but it actually is a different power than the master measured. But I don't know that because I thought my laser is stable. So I'm going to adjust my sensor that I'm in the middle of calibrating to read the same as the master read, but that's not correct now because my unstable laser changed its power while I was doing that switch. So we need that laser to be stable. It's never perfectly stable. You saw that coming. So we need to be able to quantify that. That's going to be one of the factors. Uniformity over the surface. If I, measure here or I measure here, there's always a tolerance because the absorber surface of the sensor is also made of matter. What can you do? So that's also going to be a tolerance. These tolerances we specify in all the data sheets. We know what they are. We've quantified them. We've measured them. But these are all factors that come into play. We can tighten them to a point, but never 100%. And because there is a certain sensitivity to location, that means obviously there's going to be a certain sensitivity to beam size. We try to keep that as small as we can. More important than keeping it as small as we can is at least knowing what it is. We have human beings that are made of matter that do this calibration stuff. So there's going to be a certain imperfect accuracy in the transfer from generation to generation, from the gold to the silver to the working. We quantify that as well. calibrate at a power that's somewhere in the middle of a given power scale of the sensor. When I get near the top of the scale, to what degree can I still rely on that calibration? There are going to be certain linearity effects. I calibrate at one wavelength. How correct is that calibration going to be at a different wavelength? That's not at all a simple issue. To a certain degree, it's going to depend. We have some sensor types that have a pretty nicely flat spectral response. This is one that we happen to call our P type of absorber, whatever, and it's almost perfectly flat. And so basically we calibrate this. You can't see the bottom, the x-axis here, but this is from the UV out to somewhere in the mid IR, I think 6 microns, something like that. So this is flat enough that we calibrate this at 2 points, one over here and one over here. And the calibration point over here gives us very good accuracy over this whole part of the spectrum over which the response is still flat. Here, the response is already different, so that, and so on. So when using a sensor like this, the instrument's going to prompt the user to enter, are you below whatever that crossover point is or above. Other sensor types have a very not flat spectral response. And here we need to calibrate with a full spectral curve. We use a scanning monochromator and then a few laser anchoring wavelengths. And then the user is going to be prompted to enter an explicit wavelength and not just a spectral region. So all of these things are going to determine, how far apart can the calibration wavelengths be, and if I'm far enough away, I'm not so far enough away from the calibration wavelength in the application that I'm working on that I need to change my setting, but I might be far enough away that something has changed in the accuracy. We want to know how to quantify that. If we're dealing with pulsed laser beams and energy sensors that measure energy per pulse, there are going to be frequency effects. If a given sensor can measure every pulse at up to, 10 kilohertz, as I get closer to 10 kilohertz, there are going to be some frequency effects that come into play. So all of these things, the user doesn't need to worry about the numbers, but a manufacturer of the instrument and a body that does the calibration most certainly needs to take this into account, because we need to be able to do a calculation that will eventually give us, so the accuracy in the measurement is plus minus 3%. So how did I get to that number 3%? Maybe it's 2, maybe it's 4. So I'm just going to point you in the direction of a white paper that we have on our website. If you go to the Ophir Photonics website, you go to support and you go into our knowledge center. In the knowledge center, okay, there's the first article here. I searched for the words error analysis. Ophir power energy meter calibration. Blah, blah, blah. Okay, it's a real geeky, very engineering-y kind of a title. Don't worry about remembering that. If you do a search for error analysis, the truth is, if you search for the word calibration, this I think is still going to be the first article that comes up that's written by one of our founders and our emeritus CTO. And it goes through all the calculations. You go through articles. Oh, I even had highlights. How do you like that? So this is just a snippet just to show you the sort of information that's in there. So for example, for thermal power sensors for powers up to 1 kilowatt. So here we start off with the uncertainty in NIST itself, which we know from NIST and from experience, the transfer accuracy from the gold to the silver, and so on and so on. Additional error from variations in absorption over the wavelength region, 40 plus years of historical data, we know pretty much what those numbers are, and so on and so on and so on. If you go through the numbers, you will notice, by the way, that we very much, at least at Ophir, tend to understate rather than overstate. We're fanatically conservative. That's kind of a contradiction in terms, but it works. But it's important that a potential user of a given instrument know exactly what that instrument will and will not do for you. And then there are similar calculations for higher power levels, and then for other types of sensors, pyroelectric, photodiode sensors, and so on and so on. So if that's something that's of specific interest to you, you're more than welcome to go through that. Again, that's generic information. Okay, kind of meat and potatoes. Let's look at some best practices. I'm going to start with best practices from the manufacturer's side, because I think that's also helpful for you to have an idea, and maybe it'll help you correctly and intelligently interpret what is written in a given data sheet, and maybe, you know, ask the manufacturer appropriate questions where relevant. So again, I'm going to be focusing on the things that Ophir has done over the years, because those are the ones that I'm able to talk about. So what we have done and continue to do to maximize the accuracy that can be delivered from a given measurement solution. Years back, we in-house developed, designed, and built our own manufacturing process for the discs that lie at the heart of these sensors, both the thermopile itself and the various absorber coatings. So we, you know, saw very nice improvements. I don't want to use the term the best in the industry because everybody says that, but, you know, certainly as far as we know, the best that's achievable so far in the linearity of these discs with power, phenomenal uniformity across the surface. Not perfect. Wish we could do that, but we haven't figured the perfect stuff out yet. There's some very clever tricks that we incorporated in there for calibrating energy sensors that measure energy per pulse of repetitively pulsed beams that pretty much immunize the calibration process to instability from pulse to pulse. Some pretty cool tricks. I could tell you what they are, but then I'd have to kill you. So if you recognize where that line comes from, I can probably tell you more or less how old you are, and you probably now know more or less how old I am. Over the years, we're constantly figuring out ways to further automate the process. We can never replace the incredibly talented people that do the work, but the stuff that is prone to human error, if we can immunize it as much as we can, immunize is a word that we're all very tuned into nowadays. So we've added over the years many automation steps, and we've trimmed down, if you go back, which I'm not going to do now, to that snippet from that white paper, you might notice that the transfer accuracy is 0.1, 0.2%. It used to be 0.5%. Every little 1/10 of a percent here can make a big difference. And obviously, the more lasers we have, the wider the range of powers and energies and wavelengths, the closer we can come to any given set of operating conditions, so that there are less undefined variables that can introduce inaccuracy. So we can calibrate, I won't say at every single imaginable wavelength, but, you know, if a given application works at some weird wavelength, even if we don't have a laser at that wavelength, chances are good that we have something pretty close, and again, maximize the accuracy. I just want to say something about the 40+ years experience. You know, I don't want to sound, you know, like a commercial, but the point is simply that, as we hopefully appreciate from the few examples that we just saw, a lot of know-how needs to be brought to bear in order to maximize accurate calibration. And this know-how really doesn't make itself available through shortcuts. We very often get asked, particularly, sorry to say, by newer organizations, I really don't mean anything negative with there, why did they need to buy a full-blown measuring instrument, calibrated laser power meter, whatever? You know, why can't they just buy a $1 photodiode online and build their own amplifier? I mean, you know, they've got the engineering know-how, and then they generally very quickly learn that it'll be much better for them to outsource the stuff that's not in their focus, so that they can, as I said at the beginning, concentrate on their expertise and not lose sleep because of the tools that they need to get their work done. Okay, this goes without saying. I said that I would say something about the ISO 17025, so I'm going to do that now. First of all, by way of background, in principle, accreditation by a laboratory accreditation authority, normally to this standard ISO 17025, would be applicable to a testing and calibration laboratory, one that offers specific types of testing services as an independent external laboratory. We, on the other hand, aren't that. Okay, we are manufacturers of measurement instrumentation. We calibrate our own products, really, the product that we produce as an integral, integral, whatever, part of their manufacture. Our calibrations are all NIST traceable. The traceability data is available. It can be conveyed if necessary. We've got an ISO 9000 quality system in place to support this. We've got documentation for that, if anybody, on the website and so on. That kind of goes without saying. But we do not offer external testing and calibration as a service. We offer measurement solutions. So in theory, in principle, laboratory accreditation shouldn't really be applicable, but then over the years, we kept on being asked for it. So having said all of that, it's becoming seen more and more as an indicator of a high quality calibration facility, all the nuances aside. So, go argue with the world. Our US facility and our Jerusalem facility have been ISO 17025 certified for several years. Okay, let's talk about what you can do, some real best practices. Where practical, most of them I think are probably practical to a large extent. So first of all, if you're still in the shopping stage where you're comparing specifications of different measurement instruments, shop carefully. You want to compare apples to apples. Different manufacturers use different terminology, different approaches to what they put in their data sheets and what they mean by it. You saw already some nuances like accuracy and calibration accuracy and whatever. So it's important to understand, is this an apple or is this an orange? So here's just a snippet from one of our Pyroelectric energy sensor data sheets. So as I mentioned earlier, our accuracy specs include the NIST uncertainty. We could have left that out and just quoted, specified the transfer accuracy. Our calibration technicians operate to this degree of accuracy, and that would, strictly speaking, be factually true, but it wouldn't help you, the potential user. And by the way, that NIST certainty itself is not a tiny number. It could be plus minus 0.5% up to 1.5%. That's not trivial. The accuracy, as I briefly mentioned earlier, it's a statistical number, 2 sigma standard deviation. If you don't know what that means, don't worry about it. 95% confidence level. It's not 1 standard deviation, which might have been a nicer, more attractive number. Any limitations, we write them clearly so that you know, again, what this device will and will not do for you. So for example, uniformity over the surface for this sensor, plus minus 2%, over the central 50% of the aperture, or whatever it is that it says there. Annual recalibration. This is really important. Sometimes it isn't. Usually it is. Again, all precision measurement instruments, at least the ones made of matter, drift with time and use. And so we recommend annual recalibration. Actually, for when it's a newly purchased instrument, our recommended first recalibration is after a year and a half after purchase, and then annually after that. I underlined recommend because, again, we're not calibration police. If you're in the medical equipment industry, then the FDA might be calibration police, sort of. On the back or the front or whatever it is of the product, there will be a sticker that says the last calibration date and next calibration due. And it may be a regulatory requirement to stick to that, or it may just be good sense or a market requirement. Again, every application, it depends. And by the way, the annual recalibration is for both the sensor and the meter. Some manufacturers call it a meter. We call it a meter. It's sometimes got a display, a console, controller. Again, every company uses different words. It's the output part of your measurement instrument. The meter itself is a precision measurement instrument. Granted, its contribution to the final overall uncertainty is something like plus minus 0.25% when it's new, and plus minus 0.5% if I remember it when it's old. So much less than that of the sensor, but still, if it's not periodically recalibrated, this can obviously increase and become a potential issue over time. Keep your sensor clean. That should go without saying, but it doesn't. Here you're looking at a sensor that apparently had some organic stuff splashed on it, some process debris, and that stuff got burned on the next exposure to the laser beam. Had they cleaned it when it splashed before exposing it to a laser beam, it would have come off very easily with a soft tissue and a simple a solvent like ethanol or something like that. Once it got burned on, there's no way to clean that. This sensor needed a rather expensive disc replacement. So prevention is always better than repair. If you're using a thermal type sensor, as far as possible, maintain a stable thermal environment during the measurement. The thermal sensors, at least Ophir sensors, but I would imagine that this is probably a pretty standard number. A change in temperature of as little as 1 degree Celsius per minute can be picked up by the sensor and interpreted incorrectly as part of the laser power, and it could affect the measurement. So you want a stable thermal environment. You don't want an air conditioner blowing directly on the sensor while it's measuring. For energy sensors that are measuring energy per pulse, pyroelectric sensors, those sensors can be affected by acoustic vibrations. It's actually the same physical mechanism by which they measure laser pulses. So you want to minimize acoustic noise. If you've got some heavy machinery operating elsewhere in your building and you can feel the vibrations coming through the floor, you might notice false triggering on your energy meter / sensor. You'll know if you're having it. You look at the displayed pulse repetition rate, and if it's kind of going, then you'll know, okay, there's acoustic noise. So Ophir instruments have a user adjustable threshold, so you can try to find some sort of a Goldilocks level that'll just block that level of pulses from coming in, but allow the laser pulses to, yes, come in. You can add some damping, some sponge foam or something like that between the sensor's mounting base and your optical table. Keep in mind that acoustic vibrations travel much more readily through solid material than through the air. And very often that, some simple low-tech damping like that can solve the problem. What else you can do? As far as possible, try to keep your beam centered and of constant size. We generally calibrate our sensors with the beam centered. And typically we set it up so that it fills around 1/3 of the sensor's aperture. So if you, in your measurements, also keep your beam centered and of constant size, you're eliminating a variable, namely the tolerance on uniformity across the surface of the sensor, from the measurement, and you're eliminating another potential source of uncertainty. Okay, there's my forward button. Special calibration is possible in some cases. Check with us. I read that sentence slowly and clearly, and in a second you'll see why. So what do I mean by special calibration? Okay, so you remember this overall accuracy of the calibration, meaning the overall accuracy that the sensor can deliver, depends on a whole bunch of factors. The stability of the laser, okay, that's not in our control necessarily, but we can work with that. Uniformity over the surface, and therefore if there's a sensitivity to where on the surface your beam is incident, obviously that means there's also going to be a sensitivity to how big the beam is. The transfer accuracy, the power linearity, whoops, sorry about that. All right, I moved forward a little bit sooner than I was prepared to. Okay, whatever, we'll have to live with this. The wavelength, frequency effects, and so on. So what we can do if a customer has a specific need is we can tighten some of those parameters and try to keep them out. So if you're operating at a very specific wavelength at a very specific power level, so we can calibrate at not the standard wavelength and hope that your wavelength is close enough, but actually at your wavelength if we have a suitable laser at your power level, instead of your power level being right near the top of the scale at which we normally calibrate this model of sensor. We can perhaps calibrate at exactly your power level and your pulse rate and so on. So things that we can tighten, sometimes we can do that as a special request, as a sort of partial customization of the calibration procedure so that we can remove some of those variables and tighten the final bottom line accuracy that you can get from that that particular instrument. We can tighten the allowed deviations in our standard QC check of the calibration, so that again you'll be that just a little bit closer, to the the pass-fail criteria can be tighter if in your application your customers need to see that. Now, obviously, this kind of customization, if it's possible, involves some extra level of cost, because it's going to involve some extra, some degree of special setup and so on. And now I'm just reminding you about that sentence, is possible in some cases, check with us, depends on whether we have a suitable laser and setup and so on and so on and so on. But that sort of thing can be done. It's not often needed, but sometimes it is. So I'm just mentioning it in case your application and your needs come into that not often category. Okay, we're at 51 minutes. All right, so in summary, we talked about the meaning and importance of accurate calibration, when it matters, when maybe it matters a little bit less, what kind of applications. Sometimes it's the absolute accuracy that's important. Sometimes, as we saw, maybe it's more the repeatability and so on. Every application is different. We talked a little bit conceptually about how we arrive at the accuracy specs that we give in our data sheets. And I pointed you in the direction of that much more detailed information if that's potentially of interest to you. We talked about a few things that we as a manufacturer have done and continue to do to provide instruments and measurement solutions that are as accurate as possible. And we went through a couple of best practices that I think are pretty practical and down to earth that hopefully you can adopt, as relevant to, further maximize what you can get out of whatever measurement instrument you might be using. Let's see if we have any questions. What's the difference between power accuracy and linearity with power? Okay, thanks. That's a good question. Linearity with power, basically, I increase my laser power by 3%. I expect the readout of my measurement instrument to go up by 3%. As I approach the top of my instrument scale, and typical instruments have multiple scales, eventually, to some degree or another, increasing the beam's power by 3% might lead only to an increase in my reading of 2-point-something%. So that's a decrease in my linearity. We need to quantify that. Generally speaking, the overall linearity that we specify, the tolerance of linearity from the bottom to the top, is usually maybe 1%. So it's not a big number, but it is a number. Power accuracy is the more general bottom line accuracy. You measure 3.0 watts. What's the so-called true value? The linearity is, or the lack of linearity, is going to be one of the potential factors that go into the overall final bottom line power accuracy, which also includes other contributions like uncertainty because of wavelength and frequency and all those other things. Okay, one other question. You mentioned that the various uncertainties sometimes add linearly and sometimes statistically, RSS, root sum square. Okay, I figured this question was going to come. To give a final uncertainty in the actual measurement. Can you elaborate on when the errors combine which way? Okay, so I'll give you not the short answer, but definitely not the long answer. We start off with the basic component of the accuracy, that's the calibration accuracy, and the other sources of uncertainty that go into the the measurement accuracy that we specify. By the way, in Ophir's data sheets, we usually list both the calibration uncertainty. Again, this is one of those nuances that I had to put in because of the ISO stuff. The calibration uncertainty, it shows up in our data sheet, so I just want to mention it, is that under the definitions of the ISO 17025, that refers to our calibration process itself. added to that are going to be all the other things. So the power accuracy or the measurement accuracy, that plus minus 3% includes the calibration uncertainty. A typical number for the calibration uncertainty is, I think, like 1.9%, but then there's all the other stuff. But in addition to that, there's other things that come in: uncertain, additional error with wavelength, additional error or uncertainty. I'm using them interchangeably. The QA people would probably make a face at me. Additional uncertainty, error, whatever, with, you know, all these other different things. So all of these different sources of error. The general idea is that errors that are random get added statistically, the square root of the sum of, the square root of this guy squared plus this guy squared plus this guy squared, statistically. And why is that? Because these various sources of error, which are random, one source of error might push the reading higher than the true value, but the other source of error might be pushing it lower than the true value. It's statistical, they're random. While errors that are not random get added linearly because it's a systematic error, systematic error, and their rules of statistics don't apply. So let me just give you an example. Let's say you've got measurement accuracy, power accuracy is plus minus 3%, and the tolerance on linearity is given in the data sheet is plus minus 1%, and additional error with frequency 1%. So is it 3 plus 1 plus 1, or is it the square root of 3 squared plus 1 squared plus 1 squared? So because each of these are random, it's the square root of 3 squared plus 1 plus 1 squared, which comes out to something like plus minus 3.3% instead of 3%. On the other hand, if you're operating near the top of your power scale, so that the linearity is no longer random, you're pushing to a limit, so we already know what effect that's going to have. Or you're operating near the maximum rated frequency of the sensor, so again, that's already not random, so then the errors need to be 3 plus 1 plus 1, and the measurement accuracy, the bottom line, will be plus minus 5 and not plus minus 3.3%. So I hope that was clear. Okay, we still have like 2 more minutes. Do you measure laser fluence for high power lasers, and how? Laser fluence, I think everybody uses that the same way. Fluence means power density as opposed to power. So we have sensors that measure that directly, but the truth is any power sensor can be used to measure laser fluence. You measure the power and you divide by the area. So if it's, let's say, a wide beam that overfills the sensor, let's say you're measuring a solar simulator, so you're not measuring the total power, you're measuring the power density on a specific area. So what you do is, let's say a solar simulator, you put the sensor there, you're measuring a certain power, you divide that by the area of your sensor's aperture, and that'll give you the fluence. If it's a thermal sensor, you might need to make sure to block any of that power from reaching the body of the sensor, because that could cause unwanted heat flow in the sensor, which will mess up your measurement and so on. Okay, one more question. What's the most accurate method for measuring the laser spot size? Okay, I didn't go into another one of our power lines, which is beam profilers. We've got a whole line of instruments that measure the spatial distribution of power in the beam's cross section. One way of doing that is just with a CMOS or CCD camera and a lot of really sophisticated software and a lot of optics. And there's rotating slits. It's a whole other discussion. I'm glad you asked that, because that's a good question. There are ways to, like, quick and dirty ways to measure laser spot size. At Ophir, we have some sensors that sort of measure spot size at the same time as power. We call them PPS, power position size, if you want to look for that. But the accurate way of measuring the size of your beam is, without question, by using a beam profiler, a suitably selected one, obviously. Thank you, everybody, for being with us.